Hello dear students, so let us continue our discussion on limit points. So in last lecture I had given you some exercises to show that the limit points are show that A and B are limit points of say open interval a comma b. Okay. How to justify this? We will also show that every point inside AB is a limit point of AB. Okay. That also will show. Okay. First let us try this. So to show that A is a limit point, what I have to do, you consider this open interval a to b. To show that A is a limit point, what I need to show? I need to show that whatever epsilon neighborhood or open interval we take with center at A, we will always get at least one point from the set AB, okay, inside that epsilon neighborhood. Okay, so let epsilon greater than 0. Okay, and we consider the epsilon neighborhood that is the open interval of A, that is open interval A minus epsilon to A plus epsilon. Okay, so our aim is to show that we can find at least one point from the set AB which is there inside this epsilon neighborhood. Okay, epsilon is any arbitrary positive real number. So it may happen that A plus epsilon is somewhere here inside AB. It may also happen that A plus epsilon is somewhere here. Okay, so if A plus epsilon is greater than or equal to B, then we can take any point inside the set AB, inside the open interval AB. So that particular point will lie in the open interval A minus epsilon to A plus epsilon also. Okay, we can choose any point inside the open interval AB. Okay, if A plus epsilon is greater than or equal to B, but if A plus epsilon is less than B, okay, in that case we cannot choose any arbitrary point of AB and say that it is inside A minus epsilon to A plus epsilon. Okay, that may not happen, right? So if your A plus epsilon is somewhere here, we will choose some point which lies between A and A plus epsilon. Okay, maybe we can take some point like A plus epsilon by 2. Okay, so that will be a point which lies between A and A plus epsilon. Okay, and it also lies in the open interval AB. Okay, so that way we have to separate the cases. So if A plus epsilon is greater than or equal to B, then the point A plus B by 2. Okay, we have taken a point which is inside the interval AB. So A plus B by 2 is a point which is inside the interval AB, right? A plus B by 2 belongs to the open interval AB, and A plus B by 2 also belongs to this interval. A plus B by 2 also belongs to this A minus epsilon to A plus epsilon, this interval. Okay, why? Since A is always less than A plus B by 2. Okay, A plus B by 2 is the arithmetic mean of A and B, and this B is already less than or equal to A plus epsilon. Okay, that means A plus B by 2, it lies between A and A plus epsilon. Okay, so it is inside the interval A minus epsilon to A plus epsilon. Okay, so if A plus epsilon is greater than or equal to B, we have already got a point inside the set AB which belongs to this epsilon neighborhood. Okay, now the other case is if A plus epsilon this is less than B. Okay, already we have A is less than or equal to A is less than A plus epsilon. No? Okay, so A plus epsilon cannot be somewhere to the left of A. Okay, because epsilon is already positive. So we just need to consider this case where a plus a plus epsilon is, yeah, this one, strictly less than b. Then the point a plus epsilon by 2. Okay, so this is a point which lies inside the open interval AB. Okay, why? As a plus epsilon by 2, this quantity is strictly less than a plus epsilon, which is strictly less than b. Okay, and a is already less than this. A less than a plus epsilon by 2, and a plus epsilon by 2 is strictly less than a plus epsilon, right? You can just take the difference. The difference is epsilon by 2, which is positive. Okay, so that means this a plus epsilon by 2, this is a point which lies inside the open interval AB, and it also belongs to that interval. Okay, a plus epsilon by 2, it also belongs to this interval, a minus epsilon to a plus epsilon. Okay, why? Because a plus epsilon by 2 is already less than a plus epsilon. Okay, so we have got a point inside the set AB which also belongs to this epsilon neighborhood. Okay, so in either case a minus epsilon to a plus epsilon contains at least one point of AB, one point of the open interval AB are different from A, Okay, so therefore A is a limit point. A is a limit point of the open interval AB. Okay. So similarly, we can show that B is also a limit point. So you take b minus epsilon to b plus epsilon. Take any interval of the type b minus epsilon to b plus epsilon. So that, right. So b minus epsilon may be somewhere here. B plus epsilon will be somewhere on the right side. So it may happen that b minus epsilon is somewhere here also. So we have to consider two cases. If b minus epsilon is less than or equal to a, okay, then what happens? Any point inside this interval will satisfy that it belongs to this b minus epsilon to b plus epsilon, and it belongs to AB also. Okay, so then a plus b by 2, this belongs to AB also, and a plus b by 2 also belongs to the open interval b minus epsilon to b plus epsilon. Okay, and if b minus epsilon is strictly greater than a, then we will take something like b minus epsilon by 2. Okay, so somewhere here it is the arithmetic mean of b and b minus epsilon. Okay, b plus b minus epsilon whole thing by 2. So this is actually b minus epsilon by 2. B minus epsilon by 2, it belongs to this interval AB, and b minus epsilon is strictly less than b minus epsilon by 2, strictly less than b. Okay, so it lies between, therefore b minus epsilon by 2, it also belongs to the open interval b minus epsilon to b plus epsilon. So in any case, we have got a point inside the set AB, inside the open interval AB, which also lies inside the epsilon neighborhood b minus epsilon to b plus epsilon. Okay, so B is also a limit point. So please write it yourself. Okay, the language is very similar to whatever I have written for this A. Okay, so we will also show that the derived set of open interval AB, okay, open interval AB is actually closed interval AB. Okay, so every point inside the set AB as well as the endpoints are limit points of the open interval AB. Okay, so for endpoints I have already shown, right? For the endpoints A and B are limit points Okay, already we have shown as shown, right? Now we will just show that any point inside the open interval AB is also a limit point. Okay, now let x belongs to open interval AB be any point. Okay, let x belongs to open interval AB be any point, right? So what I have to show? I have to show that whatever and I'll take and let epsilon greater than 0. So with x as center, we will consider an epsilon neighborhood. Okay, so we consider x minus epsilon to x plus epsilon. I have to show that this epsilon neighborhood will contain at least one point of AB which is different from x. Okay, right? So in this case also, let us have a look at the diagram. This is the set AB, and you have a point somewhere here, say x. Okay, and you construct an epsilon neighborhood, x minus epsilon to x plus epsilon. Okay, to show that x is a limit point, what I have to show, every epsilon neighborhood containing x, centered at x, contains at least one point of this open interval AB. Okay, which also belongs to the epsilon neighborhood. Okay, so we have to construct a point inside this open interval AB. Okay, so it may happen that x minus epsilon is somewhere here, or x plus epsilon is somewhere there. Okay, so if x minus epsilon is less than or equal to a, then we can take any point inside the open interval, or we can just take x plus a by 2. Okay, somewhere here x plus a by 2. So that will be a point which lies inside the interval as well as inside the open interval AB. Okay. If x plus epsilon is greater than or equal to b, then also we can take just the midpoint of x and b. That will work for us. Okay, and if neither of this happens, that x minus epsilon is also inside and x plus epsilon is also inside. Okay, in that case we can just take x plus epsilon by 2, which is a point inside the open interval AB and as well as inside this epsilon neighborhood. Okay, so that is the basic idea. So we consider x minus epsilon to x plus epsilon, this epsilon neighborhood, and we will show that this we will consider the different cases. So if x plus epsilon is greater than or equal to b, then the point x plus b by 2, this belongs to AB, satisfies x plus b by 2 belongs to x minus epsilon to x plus epsilon also. Okay, as why does it satisfy? Because x plus b by 2 is already, x is strictly less than, x minus epsilon is strictly less than x, and x is less than x plus b by 2, and x plus b by 2 is already less than b, and b is less than x plus epsilon. B is less than or equal to x plus epsilon, right? So we have got a point which is inside this epsilon neighborhood also, and it is also inside the set AB. Okay, right? And if x minus epsilon is less than or equal to a, okay, and then the point a plus x by 2 belongs to AB, satisfies x plus a plus x by 2 belongs to x minus epsilon to x plus epsilon also. Okay, as what happens, x minus epsilon, this is already less than or equal to a, and a is strictly less than a plus x by 2, and a plus x by 2 is again less than x, right? Because we had taken x from the set what, x is from the set AB, so A less than x less than B. Okay. So this is already there, and this x is already less than x plus epsilon. That means this quantity a plus x by 2 actually lies between x minus epsilon to x plus epsilon. Okay. So if the right side of this interval x minus of the epsilon neighborhood is greater than or equal to b, then this point will serve our purpose. Okay, we just have to find at least one point which belongs to this epsilon neighborhood. Okay, if the left side is less than or equal to a, then this point will serve the purpose. And now if x minus, if a is less than x minus epsilon less than x plus epsilon less than b, means both of them lie inside the open interval AB. Okay, say less than x plus epsilon. Right. So then we can just take then the point x plus epsilon by 2. This belongs to this interval AB. Satisfies x plus epsilon by 2 is in x minus epsilon by epsilon to x plus epsilon also. Okay, as what happens, x minus epsilon is less than x plus epsilon by 2 less than x plus epsilon. Okay, right. So this x plus epsilon by 2, it lies between x minus epsilon and x plus epsilon. Right. So in all possible cases, in all the cases the epsilon neighborhood of epsilon neighborhood x minus epsilon to x plus epsilon of x contains at least one point of the interval AB different from x. Okay, so x is a limit point. So that means any arbitrary point of AB is a limit point. Okay. So therefore the derived set of AB, we have already shown A and B are limit points. Okay. Now we will we have also shown that every point inside AB is a limit point. Okay. So the derived set is every point of open interval AB together with the this endpoints, right? So in a similar way, you can just try, or you can just remember derived set of this, say, left half open interval. This is also closed interval AB. Okay. Derived set of say right half open interval. Okay, this is also closed interval AB. Okay. So we have seen the derived set of some standard sets. Okay. 1 by n also we had seen, and then we have also seen 1 plus 1 by n. Okay, that set also we have seen. Okay, so if somebody gives you this question, what is the limit point of this, say 2 plus 1 by n, such that n belongs to natural number? So I hope you will be able to answer 2 is a limit point of this set. 2 is a limit point. Okay, so it may happen that a limit point of a set has only one limit point. Okay, it may happen that way. It may also happen that a set has infinitely many limit points. So in this case, in the case of open intervals, it has infinitely many limit points. Okay. So one thing you observed, that the derived set of A may not be a subset of A. Okay. In general, the derived set of A may not be a subset of A. Say for example this one. Right. Oh, here I did not show that any point if x is greater than b, then it cannot be a limit point. So that is actually simple. I have to show that also. If x is greater than b, then it cannot be a limit point. Say x is somewhere here, then it cannot be a limit point. Why? It's quite simple. You take the interval, so I have to find a epsilon neighborhood which does not contain any point of AB. Okay, so what you do is you take epsilon as this one, half of this distance, half of mod of x minus b. Okay, this distance. So mod of x minus b is this distance. You take epsilon as half of this distance, even exactly equal to that distance will also work. So you take epsilon equal to half of that distance, then this epsilon neighborhood, it will not contain any point of this AB. Okay, because whatever point you take here, the difference between y and that x will be less than half of mod of x minus b. Okay, so the distance whatever point you take here, it will not belong to the open interval AB. Okay, it will not be less than b. Okay, because any point here, it will be like greater than any point here, it will be like greater than b plus x by 2. Okay, less than x, less than b b plus x by 2, and this distance will be x plus x minus b by 2, right? So it is 3x minus b by 2. Okay, whatever it is, so it will be lying between these two. Okay, so this is strictly greater than b. B is strictly less than b plus x by 2. Okay, so no element of this set is greater than a particular element of this set. Okay, so in that case, we have found out an interval which does not contain any point of the set AB. Similarly, if x is strictly less than a, then also it cannot be a limit point. Okay, you just construct this epsilon neighborhood with length as half of a minus x by 2. Okay, half of a minus x, then this interval will not contain any points of the interval AB. Okay, so that is the thing. So that is why the derived set of this closed open interval AB is closed interval AB. The derived set of closed interval AB is also closed interval AB. Okay, derived set of closed interval AB, this is also closed interval AB. Okay, so you observe that derived set of A may not be a subset of A in general. Okay, right? So in fact, the derived set may contain some points which are not inside the set also. Say for example, this one, 2 is a limit point, but 2 is not a point of this set. Okay, so there are some special sets for which derived set of A becomes a subset of A. Okay, and those sets are said to be closed sets. Okay, so the next definition that we'll do is the definition of closed set. What is a closed set? So a set capital A subset of R is said to be closed or is closed if it contains all its limit points. If it contains all its limit points, okay, that is the derived set of A is a subset of A. Okay, derived set of A is a subset of A. Okay, so if a set contains all its limit points, then we say that it's a closed set, right? So for example, this one, derived set of a finite set. Every finite set is closed, right? So we can show it this way. Derived set of this set, say 0 1, okay, is actually phi, and phi is a subset of 0 1. Okay, so 0 1 is a closed set. 0 1 is closed. Okay, because derived set is empty. So in particular, whenever the derived set of a set is empty, that particular set is in closed set. Okay, so if A is finite, if A is finite set, we have already seen finite set do not have any limit points. So if A is finite, then derived set of A is empty, so this is a subset of A, right? So therefore A is closed. So every finite set is closed. A is a closed set. So there is other way of showing that also, we will do it. Okay, what about n, whether n is closed or not? The set of natural number n is closed or not? We have seen that the natural numbers do not have any limit points. So derived set of natural number is phi, and phi is a subset of n. So therefore n is also closed. What about R? R is closed or not? What are the limit points of R? Yeah, that one I did not discuss. The limit points, every real number is a limit point of R. Okay, R is the whole set of real numbers. If you take any real number from R, whatever interval you take, whatever epsilon neighborhood you take, it will always contain real points, say x plus epsilon by 2. Okay, this is a point inside this, and it is also inside R. Okay, so the set of real numbers is by default it is it has all its limit points. Okay, whatever real number you take, you can and whatever interval epsilon neighborhood you take, it will contain at least one point of real numbers. Okay, because the definition itself, the definition of interval itself, it gives us that it's a subset of R. Okay, so R is the universal set for our real analysis. So every such interval that we take is a subset of R, so it contains many points which are there in R, right? So the set of real numbers is actually a closed set. Okay, because the derived set of R is R. Every real number is a limit point of R. Okay, so you may note it somewhere. Every real number is a limit point, is a limit point of R. So by definition itself it follows. So how do you justify? Let x belongs to R and epsilon greater than 0. Then x minus epsilon, x plus epsilon, this interval is itself a subset of R. Okay, so it contains, in particular, so let us find out one point which is there in this. In particular, say x plus epsilon by 2, this belongs to R also, and x plus epsilon by 2, which is not equal to x, it is different from x, it belongs to x minus epsilon to x plus epsilon also. Okay, so every real number is a limit point of R, so it's very simple to justify, right? What about phi? Phi is closed or not? So that also we have seen. The set of derived, the derived set of phi is phi. Phi has no limit points, so we have already seen that. Okay, so phi is a subset of phi itself, so phi is also closed. Okay, so we have seen so many examples of closed sets. R is closed, derived set of R is R, which is also a subset of R, right? Okay, so there is another way of formulating closed sets, that is, a set is closed if its complement is open. Okay, so that also we will discuss. Okay. So before that, let us do some properties of this sets. Okay. Okay, so before that, let me also give you the definition of closure of a set. Closure of a set. Okay, so let A subset of R, and the closure of A is denoted and defined as a closure equal to A union derived set of A union dA. So it's the union of A with its limit points. Okay, so A closure contains elements of A together with the limit points of A, right? Say what is R closure? R closure is R set of real numbers union with the derived set of R. Okay, so what is that? Derived set of R we have already seen, it's R only. So R union R is R. So R closure is same as R, right? What is phi closure? Phi closure is phi union derived set of phi. So derived set of phi is already phi, we have seen. So it's phi union phi, that is phi. Okay, like that. Then say what is the closure of this open interval AB? So it is actually open interval AB union derived set of AB. Okay, so what is that? It's open interval AB union derived set of AB means closed interval AB. So AB union closed interval AB, open interval AB union closed interval AB, that is actually closed interval AB. Okay, right? So that is actually called closure of the set A. Okay, so let us try some more properties of derived sets. Properties of derived sets. Okay, so number one, let us try to show that if A is a subset of B, then this will imply that derived set of A is a subset of the derived set of B. Okay, right. So how to show this? The proof. Right, so we have to take an element from dA and try to show that it's an element of dB also. Okay, so let X belongs to derived set of A, be any point. Okay, so this means what? X belongs to dA means what? X is a limit point of capital A, right? That means what? Every epsilon neighborhood of say x minus epsilon to x plus epsilon of X contains at least one point of A different from X. Okay, so that is x minus epsilon, x plus epsilon, intersection with A difference X. Okay, so this should be non-empty. Okay, so means there is at least one point which is common between x minus epsilon and x plus epsilon and A minus X. Okay, because the point has to be different from X, right? But we know that A is a subset of B. Okay, but given that it is given that A is a subset of B. That means when I say that every epsilon neighborhood of X contains at least one point of A, so that one point is also a point of B because A is a subset of B. So the same statement can be reformulated as every epsilon neighborhood of X contains at least one point of B different from X. So points of A are points of B as well. Okay, are points of B as well. Okay, so therefore every epsilon neighborhood of X contains at least one point of B. At least one point of B different from X. Different from X. Okay, so therefore X is also a limit point of B also. Okay, that is X belongs to derived set of B. So we started with X belongs to dA and we have got X belongs to dB. So therefore ultimately derived set of A is a subset of derived set of B. Of course, the other way it may not be true. If derived set of A is a subset of derived set of B, it doesn't necessarily mean that A is a subset of B. Okay. Right. For example, we have seen derived set of say open interval 0 1 is closed interval 0 1. Okay. So this is a subset of say derived set of we have seen derived set of closed interval 0 1 is a subset of is equal to 0 1, which is a subset of 0 1, and this 0 1 we can consider it as derived set of open interval AB. Okay, so you take this as A, take this as B. So derived set of A is a subset of derived set of B, but A is not a subset of B. 0 1 is not a subset of 0 1. Okay, so the other way it is not true, right? If A is a subset of B, then derived set of A should be a subset of the derived set of B. Okay, otherwise it's not true. Okay, so this is one example, and also we have this exercise or this property, the second property, derived set of the union. Derived set of A union B is same as derived set of A union derived set of B. Okay. You start with an limit point of A union B. Okay, so then it will be a limit point of A also. So we can use the earlier result. We have A is a subset of A union B. So this will imply derived set of A is a subset of derived set of A union B. Okay. Similarly, B is also a subset of A union B. This will imply that derived set of B is a subset of derived set of A union B. Okay. So if we combine them, we can write it this way: derived set of A union derived set of B. This is a subset of derived set of A union B union with derived set of A union B. Okay, but this is the union of the same sets. So it is the set itself, derived set of A union derived set of B. This is a subset of derived set of A union B. Okay. So one part we have done. Now the other part. Okay, how to proceed with the other part. Right. So the other part is we have to start with a element from derived set of A union B. Okay. So let X belongs to derived set of A union B. Yeah, it may happen that derived set of A union B is empty. Okay, in that case it's automatically a subset. Oh, okay, I should have written it here also, in the earlier one also. Okay, maybe you can write it somewhere here. This one, if derived set of A is phi, okay, if it is empty I cannot take an element. Okay, so if derived set of A is phi, then phi is already a subset of derived set of B, right? Phi is a subset of any set, so that is derived set of A is a subset of derived set of B. Okay, we don't have to show anything. So let derived set of A is non-empty. Okay, then we start with an element of derived set of A. So please add that part. So here also let us do it that way. If derived set of A union B is equal to phi, then derived set of A union B is already a subset of derived set of A union derived set of B. So even if the sets on the other side, that is the right hand side, are phi, then also there is no problem. Phi is a subset of phi only. So let just cut this part. Let derived set of A union B is non-empty, okay, not equal to phi, and let X belongs to derived set of A union B. Okay, so this means what? this implies X is a limit point of A union B. Okay. So I have to show that X is either a limit point of A or a limit point of B. Okay. So X is the limit point of A union B. That means what? So this means every epsilon neighborhood of X contains at least one point of A union B. Okay, but the points of A union B are either the points of A or the points of B. Okay, so it may happen that every epsilon neighborhood of X contains points of A, or every epsilon neighborhood of X contains points of B. Okay, so X is either a limit point of A or it is a limit point of B. Okay, so we'll just write that part. But A union B consists of points of A or of B. Okay, so every epsilon neighborhood of X contains at least a point of A or of B. Okay, so that is, this means that what, X is a limit point of A or X is a limit point of B. Point of B. Okay, so X is either a limit point of A or it is either a limit point of B. Yeah, but no, I think we need to do it in a different way. So every epsilon neighborhood of X contains at least one point of here, as we change the value of epsilon, okay, it may happen that the point that we choose once it is from A, another times it is from B. Of course, there is another result that X is a limit point if every neighborhood, epsilon neighborhood, contains infinitely many points of in B. That, but of course, I have not done that. Okay, let us do it in a different way. We'll consider the contrapositive. Okay, and try that. I have to show that derived set of A is a subset of derived set of A union derived set of B. Okay, so the other way we'll try that if, so I wanted to show that if X is a limit point of derived A union B, then this will imply that X is a limit point of A or X is. So let us try the other way, contrapositive, that is X is neither a limit point of A nor a limit point of B. This implies that X cannot be a limit point of A union B. Okay, so let us try that. That will be a better way of proving it. Okay. So so we show that derived set of A derived set of A, yeah, we show that if X doesn't belong to dA union dB, then X doesn't belong to derived set of A union B. Okay, this is what we will show. So if X does not belong to dA union dB, and this means what? X is not a limit point. X doesn't belong to dA also, and X doesn't belong to dB also. Okay, it doesn't belong to dA, doesn't belong to dB also. That means X is not a limit point of A, and X is not a limit point of B also. Okay, so that means what? X is not a limit point of A. This means what? There exists say epsilon greater than 0, such that this epsilon neighborhood, okay, such that x minus epsilon to x plus epsilon, this neighborhood doesn't contain any point of A. Okay, doesn't contain any point of A different from X, okay, and there exists for X is not a limit point of B. That means there exists some, say, delta greater than 0, such that x minus delta to x plus delta, this doesn't contain any point of B different from X, okay. So we have got two neighborhoods of X. X is somewhere here. We have got something like x minus epsilon to x plus epsilon. This neighborhood doesn't contain any point of capital A. We have got something like x minus delta to x plus delta. This neighborhood doesn't contain any point of capital B. Okay, so which portion should I take so that I get an epsilon neighborhood which doesn't contain any point of A union B? Okay, so if I take x minus delta as per this diagram, if I take the larger neighborhood, okay, then it will not work, because the larger neighborhood doesn't contain points of A, points of B, but it may contain points of A, right? But the smaller neighborhood, it doesn't contain point of A, and since it is a subset of x minus delta to x plus delta, it doesn't contain points of B also. Okay, so I have to take minimum of this two, right? So we take let me rename this. Let's delta, let me write this one as delta 1. Okay, x minus delta 1 x plus delta 1, and this one is delta 2, x minus delta 2 to x plus delta 2. Okay, so let epsilon equal to, so this is say delta 1, this is delta 1, and this is delta 2, delta 2. Let epsilon equal to minimum of delta 1, delta 2. Okay, then the epsilon neighborhood x minus epsilon to x plus epsilon does not contain any point of A union B. Contain any point of A union B. Okay, so therefore what? X is not a limit point of A union B. Okay, so therefore derived set of A union B, this is a subset of derived set of A union derived set of B. There are two ways of showing subsets. A subset of B, we can show it either by taking x belongs to A implies x belongs to B, or we can show it if x is not there in the larger set, it is not there in the smaller set. Okay, if x doesn't belong to B implies that x is not there in A also, then also we can show that A is a subset of B. Okay, right, so this is another way of showing. So derived set of A union B is a subset of derived set of A union derived set of B. So if we combine that, those two results, we can conclude derived set of A union B is exactly equal to derived set of A union derived set of B. Okay. So that is the proof. Okay, so the second part is non-trivial. Okay, the first part was just the application of the earlier result, right? So, but the same is not true for intersections. We'll see. The same result is not true for intersection. Okay, maybe you can try this. Derived set of A intersection B. This is a subset of derived set of A intersection B. This is a subset of derived set of A intersection with derived set of B. Okay, but the other way it is not true. But derived set of A intersection with derived set of B may not be a subset. Okay, may not be a subset of derived set of A intersection B. So you try finding out some examples. Derived set of A intersection derived set of B may not be a subset of derived set of A intersection B. Okay. So one hint maybe I can give you that you have already seen the intervals. Okay, so say 0 1 and you take another interval 1 2. Okay, so you take this as the set A, this is the set B. What is the derived set of A? You will see it's closed interval 0 1 and derived set of B is actually open closed interval 1 2, closed interval 1 2, right? So what is their intersection? Closed interval 1 2. So derived set of A intersection with derived set of B, this is what? This is actually singleton 1, right? Singleton set 1. But this is not a subset of derived set of A intersection B. What is A intersection B? The intersection of these two intervals is actually empty, so it's phi. So singleton 1 is not a subset of phi. So that example. So I have already given you almost the idea. Okay, so please write it yourself. And the part of this proof is quite simple. A intersection B, you know, it's a subset of A. So just apply derived set of A union B. A intersection B is a subset of derived set of that. A intersection B is also a subset of B. Okay, so just apply that and then take the union of both sides. Okay, so that way you can prove it. Okay, so in the next lecture we'll do some properties of closed sets, right?